Welcome back, guys. So we're going to pick up where we left off in chapter 5. So we stopped at doing an exercise from calculating the atomic weights from the isotopes of the element under percent abundance. So we're going to continue where we left off. And we're going to do this next active exercise where we calculate the atomic mass of sulfur, symbol S, using the data from 5.2. So the data from 5.2, let's just quickly go over there. So let's share the PowerPoint. So if we go back a slide, we can see this has a table of a percent abundance of some natural isotopes, and the values we want to use are right here. So let's go back to our whiteboard here, and let's start this problem. Okay, so we are going to calculate the mass of sulfur. So let's go. So the way to do this is we take our we're going to take each of our percent of the isotope and multiply it by that isotope's mass. So it's important you always try to convert these to percentages. Otherwise, you'll have to remember to divide your final answer by 100. So 30.35 U. Okay, that's the first one. So you're just going to do this for all the isotopes. Okay, times 0.0076. 0.251 atomic mass units. All right, we keep going here. 33.967 8663. Oh, sorry, 83 times 0.0429. So let's just erase this and draw it nicer. 683 equals 1.457 U. Okay. Then lastly, we have 35.967 0.88 times 0.0002, so very small abundance of this isotope, and the contribution to the mass is very small. Okay. So now what we do is we add these all up, and we should get 32.065 U. And around 32.07 is what you see on the periodic table for the molar mass, sorry, not molar mass, the atomic weight for sulfur. We will talk about what molar mass means. You may have heard of it in high school chemistry, but we'll talk about that much later. So 32.065 atomic mass units. So hopefully that was okay. It was just a further extension of what we did in the previous two exercises on Tuesday. The same procedure, same mathematical operation here. Okay. Based on their atomic masses. And when they were doing this, they found that certain properties, repeat at regular parts of the periodic table or intervals. And that's another useful thing for the periodic table, because we can associate a group of atoms or elements having specific properties at regular intervals. And one thing to note that the arrangements were not perfect. At first, according to their atomic masses. So the arrangements were not perfect. So as time go on, we fixed them. So the things about the arrangements is that there were errors in the atomic masses. There were errors in atomic masses. And they were able to correct this by rearranging it. So the correct order of things, ordering property is based on the atomic number. Is the atomic number. So that's why when you look at periodic table, you see from right to left, it goes 1, 2, 3, 4, 5, 6, 7, 8, and that's based on the atomic number. Okay, so let's look at a picture of the periodic table. I'm going to share screen again. So here we have a picture of I keep saying atomic. Picture of the periodic table of the elements. So the periodic table you'll be given is kind of similar to this. I actually like this one a lot more. I may actually use this one, but you see here you'll get the symbols, element symbols. The top number is the top number above the symbols. For example, boron is 5. That means that's an atomic number, so it has 5 protons, and also 5 electrons. And the bottom number is its average atomic weight, so that is where the isotopes come in to play, and that gives us our average atomic weight. So you'll notice that there's some numbers above the boxes, like 1A, 2A. So in the US, we refer to the groups in a different numbering scheme than the IUPAC, or what internationally is accepted. And how I've learned chemistry is based on that system too. I do not say column 1 versus to column 18. I usually go from if we start from the hydrogen and going forward, I say 1, 2. You don't need to worry about transition metals too much about their group names, because I rarely cite them. But the transition metals have their own set of numbers from 3 to 8, and then 1 to 2B. So it's kind of confusing. So I will kind of ignore those. So if we go to the rightmost block, we can see there's numbers from 3 to 8A, and those are mainly the group numbers. So they are called group or family numbers. So we'll talk more about those numbers, but usually for now we will just refer to them by another name. So there's usually specific names for each of the columns, so we'll refer for now to those names because it might be easier at this point to remember them by. Okay, so that's the periodic table. Let's move on here. Okay, so let's talk more about what the periodic table, what the information means, because I might have glanced over it a little bit too quickly. All right. So, sorry, let's move on here. So we have, all right. So here's a sample box from the periodic table. So we have a box that indicates an element. So on the top here, we have a number, then we have a symbol, and then we have a number at the bottom, a much larger number, like so. So let's say here, all right, this number on the top is my atomic number. So that gives me the identity of the element. Right here, this two-letter symbol here is called the chemical symbol. So you'll need to know the chemical symbol and the name, be able to interpret them when you come across a quiz or exam. And then lastly, we have at the bottom is the atomic mass. All right. So this is all the information we expect to know. So that is a sample from periodic table. Go on. All right. So let's talk about the rows and columns of the periodic table. So a period. So periods. So the periods are the boxes arranged in horizontal rows. So as we go across a periodic table, those are called periods. So boxes arranged in horizontal rows, sorry. So we numbered them from top to bottom, numbered. From top to bottom, and they vary in length. They vary in length. Though, for example, the first period, you know, it only has the hydrogen and the helium elements, so it only has two elements in there. So as you go down the periodic table, the rows will definitely vary, and they are based on the atomic number and the certain properties that each vertical column represent. Okay, so now let's talk about groups. So groups are also called chemical families. What I was mentioning earlier. So they represent a chemical family, and they're represented by family because they have similar, usually similar certain properties. So we say they are elements with similar properties. Placed in vertical columns. In vertical columns. So they are identified by two rows. Of numbers. Across the top of the table. So the periodic table, I give you, I believe they will have these numbers, so you don't need to memorize the numbers. Just know, like, when I ask you a question in group, like group 6, you can find on the periodic table group 6, but I should be able to give you these numbers so you know where to find them. I'm not going to have you memorize those group numbers or like the two rows of numbers. I'm not going to make you do that. All right. So main group elements. So let's talk about what those are or where to find them. So they are the representative elements in the periodic table. Representative elements. So they are elements from one of the A groups. So the A groups are the main group elements, and the B groups, those are what we call transition metals. We won't talk about them yet. A groups. So we have 1, 2, and 13 to 18. Also known as 1A, 2A, and 3A to 8A in the periodic table I showed you. So they're also represented by those numbers. Like I said before, how I learned about these groups, I categorized them as A and B. So I use the US notation, but it's up to you, whatever notation you need, you use. It's just because there's certain concepts in chemistry that I've linked with these group numbers, and they help me understand it better. But we can talk about what that means later when we come maybe to an example of that. All right, let's move on. So that's periodic table and a good introduction. Okay, so let's talk about some other parts of the table. So now we have transition elements. So they are known as transition elements because they can take on more than one, let's say, charge in various compounds. Those are what we call like transition elements. So in this case, they are called transition metals. Stuff like nickel, iron, platinum. So those metals that we often kind of hear of in the real world, they are known as transition metals. And general chemistry is a brief overview of transition metals, or in what we call inorganic chemistry. So they are the elements. Elements in the B groups. B groups. So groups 3 to 12. 12, or 1B to 8B. All right. Let's just double check that I got that right. 3 to 12. So 3 to 12 here. So 1B, 1 and 2B to 8B. So for transition metals, it may be helpful to just remember the IUPAC nomenclature because the 8B covers 3 elements. And so that might be a little bit confusing. So I would not worry too much about the US usage for transition metals. They are a little bit confusing here. So don't pay attention to that. I am uncertain why it's called 8B. I have never really wondered or looked that up, but that might be a good point to bring back next time. Okay. So, um, so yeah, if you look at that periodic table, the nomenclature for the US is kind of strange. Okay, so but it's 1B to 8B. 8B covers 3 elements. I'm not sure why. Maybe they have similar properties. That's my guess. All right, so let's talk about what metals do. So metals, they are elements. Elements to the left of the stair step line that begins between atomic numbers numbers 4 and 5, 4 and 5 in period 2, 2 and ends between 84 and 85. So let's just go over what that means. So let's revisit our periodic table. Let's share that screen. So to the so you see here that my staircase here in bold and red font. So it looks like a staircase, and that separates the periodic table from the metals and the non-metals. So anything left left to the staircase. So the staircase encompasses the elements that are above and below the lines. So boron, aluminum, silicon, germanium, adenine, tin, antimony, not tin, antimony, tellurium, polonium, and AT. I forgot what AT is. Let me just refresh my memory. Oh, I realized I wasn't sharing. So this is the picture of a periodic table. So let's just look at what AT means. So AT is a symbol for astatine. Hold on, let me see. And then AS is arsenic. Oh, I can't believe I forgot that. Okay, never. AT is acetine and AS is arsenic. Arsenic, very bad for you. Don't. It's found in the soil. So whenever there's science saying there's levels of arsenic, you want to stay away. Okay. So to recap, to summarize again, because I don't think my screen was sharing. You have the staircase here in bold and red, and everything to the right of the staircase is considered non-metal. Everything to the left is considered metallic or metal. So the elements found on the staircase: B, aluminum, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. They are kind of a hybrid of both non-metal and metal. So we have a special name for that. But anything to the left, and anything to the left of those, like these right here, all of these guys are metals, with the exception of hydrogen. And it begins between 4 and 5 and ends at 85. It ends between 84 and 85. So it ends about like right here. So they have metallic character. Okay. So we'll come back to this periodic table in a bit. So let's talk about now. Go back to the whiteboard. Okay, so let's go forward. All right, non-metals. Non-metals elements. On the right of the stair step line. So from that picture of the periodic table, everything that was to the right of that stair step are non-metals. Examples are fluorine, oxygen, neon, chlorine, sulfur. Those are all non-metals. So just because a substance has a solid state doesn't mean it's a metal. It could be a non-metal or a metal. And lastly, we have metalloids. So they are elements that border the line. So elements that border the stair step line, that border the stair step line. And some takeaways is they have properties of both metals and non-metals. And the elements that are considered metalloids are boron, silicon, germanium, arsenic, antimony, and tellurium. So actually, polonium is not one of them. I apologize. It's not one of the metalloids. It's probably most likely a non-metal. We can actually look that up right here. Okay, so it's actually, I think, related to its metallic character. So it's actually more of a metal than it's more of a metal. So we consider it a metal, not a metalloid. But don't worry about polonium. Yeah, do not worry about polonium. We will most likely never talk about it. So that's one element you don't have to worry about. Okay. Okay, let's list the, let's go on. So let's now go to another active exercise. So we have about 15 minutes left. So let's continue. So now let's talk about an active exercise. So I want you to list the atomic number, chemical symbol, and atomic mass. Mass of the third period element, third period element in group 6A/16. So in addition, classify the element as either a main group or transition element, and either a metal, non-metal, or metalloid. So we use the periodic table to help you with this. That's why we have it for you. So now let's go over, spend a few minutes to work on this, and then come and check back as I discuss the answer. So we're going to go to group 6 or 16. And if we look at our periodic table, okay, so let's just share again, new share. All right, so group 6. So we said group 6A or 16, that is the oxygen family right there. So we see that is group 6, and we're going to go to the third period. So we count down 1 from hydrogen, lithium, then sodium is the third period. Go to 6A, that is sulfur. So that is sulfur. Sulfur is like so, sulfur. So we have, so let's go back now to the whiteboard. That's sulfur. So sulfur has, so the atomic number of sulfur is, so Z will equal 16. Z equals 16. The chemical symbol is S. And then the atomic mass of sulfur is about 32.06. Now, let's classify the element as a main group or transitional. Remember, main group is any element in the periodic table that is not part of the transition metal block. So nothing from 3 to 12 or 3B to 8B. So, and the main group metals are the groups from 1 to 2 and 13 to 18, or 1A to 8A. And we see that sulfur is part of the main group metals, so we call it a main group element. And since it's to the right of that staircase that we see here, sulfur is a nonmetal. All right, so let's go back now to the whiteboard where we can discuss our answers. So sulfur, topic number 16, the symbol is S, and 32.06 is the atomic mass, the mass number. And here sulfur is our symbol. Okay, so I think that's pretty straightforward. Let's move on. Okay, so now this exercise, we're going to study this slide. Okay, so let's look at this slide. Okay, so these are, this is called, so these are the elements. This is the table of common elements that you'll be required to know. So everything on this list, you should kind of have, you should study it well because you need to know the symbol and the element name. So be able to translate from the element name and the symbol. Don't worry about the atomic number because we'll give you the periodic table. So these are the elements you'll have to know. So we'll have a lot. We'll work on this a lot. You'll study the names. You'll be able to name compounds, and on the final last year, the naming compounds. I think a lot of people struggle with that, so I would focus on naming as an important area to study because it can be difficult. And once you name the stuff, it can, you can if you're on a date, you can sound smart and use these very complicated names to name common stuff you see in real life. And who knows, maybe your date will be a little bit impressed. That's what I thought. That's what have I ever tried it? No, I have never tried it, so I can't really comment on that. But these names are important. You'll see in Gen Chem, and you'll see it throughout your chemical journey in college and beyond if you want to study it. So be familiar with these names. All right, let's go to the next one. So what we want to do here is kind of remember this periodic table, partial periodic table. These are all the elements you're expected to know. So let's just go right from the top. So it's helpful to put hydrogen here because it's in the same row or same period as helium. So hopefully you kind of go through this table and see if you can name them all correctly, and then you can come back and hear the correct name from me. All right. So H, hydrogen, helium, lithium, beryllium, lithium. The lithium ion battery, the Energizer bunny, beryllium, boron, carbon, the element of life, nitrogen, also the element of life, oxygen, also very important, fluorine, neon. I don't know if you guys probably got their own enough, but if you go, downtown, certain places, shops and stuff, they have neon signs. And those are the neon lights. So the color neon gives that effect when passed through an energy source. Those electrons can give off the characteristic color for neon gas. Sodium, magnesium, very very important. Metal elements, aluminum, silicon, phosphorus, sulfur, both very smelly compounds, chlorine, argon. So argon gas is actually part of our atmosphere in very small amounts. Potassium, very important, found in bananas. Calcium, also very important. Help keep your bones strong. Calcium found in milk, cheese, etc. Chromium. Chromium is probably most used in car parts. Manganese. Manganese, if you heard of manganese permanganate, potassium permanganate, that's a very important chemical. Iron, cobalt, Ni is nickel, copper, Cu, zinc, Br, bromine, Kr, krypton. We're going to skip most of the other transition elements. Ag is silver, Sn is tin, so that's a weird one. Iodine, or iodine. Ba, barium, an earth metal. Hg is mercury. So mercury is toxic. We're trying to phase mercury out. I think most of it has been phased out in the lab, so you most likely won't work with mercury ever, because it's just a very, very, very toxic element. Then lastly, Pb is lead. A very weird name, weird abbreviation, but Pb is lead. So those are all the elements you want to keep in mind, because you'll have to be able to know their name and the symbol, and vice versa. Okay, so that's our periodic table of elements. That's all you need to know, and that is the end of chapter 5. So hopefully that wasn't too bad. So we have a few minutes left. Let's go ahead and start in chapter 11. That is our next chapter. So let's go ahead and do that. So I'm going to switch back to my whiteboard or my iPad. I'm going to bring up chapter 11. So in a few minutes, so we'll probably just scratch the surface of it. All right, this next chapter, though, it can be tricky. Now we're going to talk about quantum mechanics. So we talked about the nuclear model. Now we're going a step further and talk about the quantum mechanical model. Okay. So you guys ever heard of quantum mechanical model? It has to do with, first principles, like what makes up the atom, like energy, light, radiation, particles. We're going to be talking now specifically about the particles, the electrons. Okay, so let's just get started on chapter 11. All right, chapter 11, we're going to talk about electromagnetic radiation. Okay. So what is electromagnetic radiation? Well, it's energy in the form of electric because it has what's happening is electrons are part of that radiation, and magnetic waves. Magnetic because it also has magnetic properties, including, so they include the following: gamma rays and X-rays. So the one of the high energy forms of electromagnetic radiation. These rays can have the possibility of causing damage to human tissue or ourselves, living things. Gamma rays in particular, because they are what cause radiation poisoning or radiation sickness from nuclear fallout. So ultraviolet ray, ultraviolet. So ultraviolet radiation is primarily from the sun or from large I guess planetary bodies like the sun, stars. So ultraviolet. Visible. There's also visible radiation. That is what the colors we see every day, like red, blue, green, orange, white, black. Those are all the colors. So white is a combination of all colors. Black is the absence of all colors, or absence of light. So the darkness you see is where light does not reach. So that is the absence of light. Visible and infrared light. So like IR sensors and like they detect heat signatures as a source of infrared radiation. Okay. So that is time is up. We'll just finish this slide and we'll just call it a day, guys. Okay. So don't just stick with me for a little bit more. So infrared and infrared light. And then lastly, we have microwaves. So the microwaves are they're what we use in like a microwave oven. What they do is they cause rotational vibration. They cause molecules to rotate, and that releases energy, and that is what heats up your food. Because and lots of times in your food there's water. So when we excite it with microwave radiation, we are actually causing the water molecules to like kind of jolt, and they rotate and release energy, and that is what causes the gradual heating of your food. Right. So microwaves and radio waves. So radio waves are important. Radio towers, cell phones, they all emit radio radiation, and that's why we could use them for so long and not experience any downside really, because the energy associated with radio waves is so small that it does not harm our bodies. So it's just under the threshold of what our bodies can tolerate in terms of radiation, radio waves. So energy has this relationship like as a wave. So it's transmitted by the speed of light. So energy is transmitted. It's transmitted at the speed of light. Because radiation is a source of light, which is composed of these, high energy, what we say particles. Speed of light. So speed of light is denoted with C. We might have went over this before, and the speed of light is 3.00 times 10 to the 8th meters per second. So that is the fastest thing in the world. The speed of sound is slower. Nothing is faster than the speed of light, because as you turn on light, boom, a room lights up right away. So that's how fast the speed of light is. You can't even respond before the light fills the room. Meters per second. For more, I guess, relatable term, we could say it's about 186,000 miles per hour. Imagine if your car could travel that fast. You'll get anywhere like that instantaneously. But last technology is not at that level yet, so we have to stick to more realistic human speeds. So what we just described is that energy is transmitted in in what we call it's transmitted through by the speed of light, and different levels of energy are given by these sources of radiation. So this is a natural part of our world. Each of these sources of light, um, they give off energy, so that is why they are called radiation. They have energy that's transmitted, and they also have wave-like properties. So radiation also has wave-like properties that can be described by a wave equation. So the equation is like this: waves are described by properties such as velocity, wavelength, and frequency. So frequency and velocity are different. V is for velocity, nu is for the Greek letter for frequency. So the relationship is that the speed of light is equal to the wavelength times the frequency. So in this case, wavelength and frequency are inversely proportional. What that means is a longer wavelength radiation, for example, visible light, red color is around 650 nanometers, and that is within the window of what we can see. But since it's so long, it has a very short, a very low energy value that that it carries. So every time you see colorful light, light, ambient light as well, they are a long wavelength source of light because we can see the colors of the light as it shines on the room. Is very low energy radiation. Whereas gamma rays, they have such a high frequency wavelength. They have a small wavelength, and that means there's each time the wave finishes from a crest and a trough and back to the crest again, that frequency gives you a shorter wavelength per interval, and that gives you a higher energy content. But we'll talk more about the energy equation. What you should take away is that the shorter the wavelength, the higher the frequency, and the longer the wavelength, the longer the wavelength, the shorter the frequency of the wave at a certain interval. For example, if I have this interval and I have a wavelength that's very long, that frequency is very small. But if I use the same interval and I have a wavelength that's repeating, a very short repeating, you see that I reach the number of wavelengths within that certain interval is much greater, meaning my frequency is much higher. And I believe we can actually draw this right now. So what we should take away is that the wavelength and the frequency are inversely proportional. So wavelength and frequency are inversely proportional. And we can visualize this in a graph. So for example, if I have a wavelength like this, so here's my time interval. So see here, I completed the wave within this time interval. So let's say this is my interval. So my wave barely didn't even complete. It completed, here's one completion, but it didn't complete here. So the interval is only like one cycle. So here is like 1.5 cycles per interval. So this would be a low frequency, long wavelength. So the wavelength will be here. So if I start from here to say here, that is my wavelength. And so to figure out the frequency, you would count the number of wavelengths that happen per an interval. In this case, it's like 1.5 cycles. But now if I have the same time interval, but now I have an even shorter wavelength, say like this. You see here that my wavelength now is shorter. It's much shorter. And my time interval is about 1, 2, 3, 4, 5, about 6. So here's 6 cycles per my time interval. And now I have a high frequency and shorter wavelength, short wavelength. So it turns out that this wave property is characteristic of light. And next time we'll talk about the other property of light, which is light also has particle nature, and that when certain radiations give off, that energy can be quantized, or it will have a discrete or specific amount of energy associated with it. And we can solve for that using this equation, the speed of light, and also the relationship between energy and frequency. So we'll talk about that next week. All right, guys, that is, sorry for going a bit over, but have a great weekend. Stay safe. You know, the cases are ticking up, but I think that's in like the Midwest or Mid-Eastern United States. So hopefully everyone stays safe. And hopefully, you know, things would get better. But anyway, see you guys. Have a great weekend. See you next week.